right? And before we start drawing circuits, let's basically get back to our basic block diagram or the negative feedback loop. We'll do it at the block level. So now we understand that this is not just a frequency independent gain, this is a frequency dependent gain A of S, and the closed loop gain VO by VI is nothing but 1 over F times loop gain over 1 plus loop gain. This loop gain now is a function of S, right, and is simply nothing but A of S times F. So let's start with the simplest possible system. Let's say a forward amplifier which is first order. So A of S is nothing but A naught, the DC gain, and there will be a single pole. So let's call that S by omega naught. Okay, in the common source amplifier, that omega naught will will correspond to whatever 1 over RS times CGS plus 1 plus CGD times A blah 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 blah, right. Okay. So, but at this point at the system level, it just is good enough to model it by a single pole with a bandwidth omega naught. Now, what comment can we make about the loop gain function? So, the loop gain function is simply this multiplied by F, correct, and many times it is actually easier to write this as 1 over F times 1 over 1 plus 1 over loop gain of S. So, VO by VI therefore is nothing but 1 over F times 1 over 1 plus S by omega naught over A naught F S over A naught times omega. Okay. So, if A naught F is somewhat large, okay, then this is approximately equal to 1 over F times 1 over 1 plus S over A naught F omega naught. All right. In reality, I am missing a DC gain term, which is basically A naught F by 1 plus A naught F, and there is going to be a small correction even in that frequency. That correction will be of the form A naught F by 1 plus A naught F. All the I am going to to first order, they are all close to 1. So, first question. So, whenever you take a system with memory and put it in a feedback loop, we have to be worried about stability of the closed loop system, correct? Okay. So, what comment can we make about the system? Is it stable or not? Yeah. So, remember that we would have arranged the negative feedback loop so that A naught F is is basically positive, right. So, clearly the pole is in the left half S plane, alright. So, this is stable, and is it only stable for some particular values of A naught F, or is it stable for all values of A naught F as long as the sign of A naught F is positive? Yeah. So, it is basically, therefore, it is called unconditionally stable, in the sense that if you have DC negative feedback, then regardless of the magnitude of the loop gain at DC, the system will be stable, right. Okay. So, what is the bandwidth? Now let us get a little more. So, we are happy that the closed loop system is stable. Now, let us take a look at the bandwidth of the loop gain function. 3 dB bandwidth of the loop gain function. What is this? Power gain. Okay, so what is the, if power gain becomes half, what happens to the voltage gain? 1 by root. Okay, so what is the DC gain of the loop gain function? This is the loop gain function. What is the DC gain of the loop gain function? Huh? A naught F. So basically, at what frequency does this magnitude of the loop gain function fall to 1 by root 2 times its value at DC at omega naught. So the bandwidth of the loop gain function is omega naught. Okay, but what comment can, and roughly, I mean colloquially, right, when somebody says the bandwidth of this amplifier is, I don't know, 10 megahertz, what do you understand by that statement? In other words, you know, do you think if somebody gave you a bandwidth, signal with, I mean, an amplifier with a bandwidth of 10 megahertz, and said, you know, go give me a lot of gain at 40 megahertz, right? What would you say? Yeah. So basically, you know, loosely speaking, the bandwidth is a number that quantifies, you know, the frequency range over which, you know, a system is useful. Correct? So I mean, if you basically say, you know, I have a 5 megahertz bandwidth, amplifier, and somebody said, you know, I need to process 25 megahertz signal, then you say, well, this amplifier is simply not suitable, right? Because the bandwidth is only 5 megahertz. Okay, all right. So that's you know, that's what we understand by bandwidth. So you know, using that connotation, this loop gain function only has a bandwidth of omega naught. So what, I mean, this would tend to indicate that, you know, beyond omega naught, the loop gain function is falling off, you know, very rapidly at 20 dB per decade, right? So you might think that, you know, beyond omega naught, this feedback loop is simply not working because the loop gain is falling off. All right. However, if you look at the closed loop bandwidth, what is the closed loop bandwidth? A naught F times omega. All right. Okay. So what is this telling us? Yeah, the closed loop bandwidth, right, okay, is A naught F times omega naught, which is telling us that, I mean, what do you call, if you plot the closed loop magnitude response, this is frequency, you plot the Bode plot, this is this corresponds to 1 over F, and you have minus 20 dB per decade, and this basically is A naught F times omega, right? And what is the feedback loop trying to do essentially? What is the forward amplifier, or what is the negative feedback loop trying to accomplish? It is trying to make sure that V naught times F is equal to, what is the feedback loop trying to do? It is trying to make sure that V naught F is equal to Vi. All right, and if you and that will only happen if the loop gain is very large, right? So but here we see that the loop gain is starting to fall off even at omega naught, right? But and you would think that the feedback loop has stopped becoming effective beyond omega naught, right? However, as we see, the closed loop bandwidth is A naught F times omega naught, correct, which is telling us that no, the feedback loop is still effective, you know, at frequencies much larger than omega naught, right, and it only stops becoming effective around frequencies A naught F omega. So intuitively, why does this make sense? Okay. So, basically notice that the closed loop gain, right, is loop gain by 1 plus loop gain. And what is the loop gain at DC? What is the loop gain at DC? A naught F, right? So, uh, and what is 1 plus loop gain? 1 plus A naught F. So, loop gain by 1 plus loop gain at DC is almost 1, right? Now, let us say the loop gain at DC is just for, let me take a number. So, let us say the magnitude of the loop gain at DC is say 100, right. So, loop gain by loop gain plus 1 is approximately 0.99 actually, okay, close to 1. Now, let us say we look at the bandwidth of the loop. The bandwidth of the loop gain function is omega naught, correct. So, what comment can you make about the magnitude of the loop gain at omega naught? Roughly 70, right. Okay, it is actually a complex number, it is 70 angle minus 45, right. But you know that number is so much larger than 1 that what comment can you make about loop gain by loop gain plus 1, right. You know let us say something like 0.9, okay, alright. So, even though the loop gain has fallen from 100 to 70, which is a 30% change, this number loop gain by loop gain plus 1 is 0.98, right. Now, let us take the magnitude of the loop gain at 10 omega naught. What is the magnitude of the loop gain at 10 omega naught roughly? Roughly estimate is approximately 10, right. And what will be the angle of the loop gain at 10 omega naught? Yeah, it will be roughly about you know minus 90 degrees. But again, we'll to get an estimate, we'll just hack it, right. Loop gain by loop gain plus 1 is approximately 10 by 11, which is about 0.9, correct. So, you can see that even though the magnitude of the loop gain has fallen from 100 to 10, this number loop gain by loop gain plus 1 has only fallen by 10%, right. Okay. So, when will this party stop? This is basically saying that you know you can keep reducing loop gain and we do not seem to see much effect in the magnitude of the closed loop gain. So, when will this when will this start falling? I mean, in other words, when will this stop becoming close to 1? Yeah. So, basically when the magnitude of the loop gain starts becoming comparable to 1 is when this quantity loop gain by loop gain plus 1 will no longer be 1, correct. So, therefore, so what is therefore the so what is therefore the resolution of that surprising seemingly surprising fact that the loop gain has started falling off at omega naught already, but and therefore we originally thought that the feedback is breaking even at omega naught, right, and therefore the loop apparently seems to be, I mean, should not work, but it seems like but the loop is actually working, the feedback is working quite nicely even up to frequencies as large as A naught F omega naught. So, what is the so now since we have seen this argument, what is why is this happening? So, it is true that the magnitude of the loop gain is falling dramatically beyond the loop gain's bandwidth, which is omega naught. However, the magnitude of the loop gain we started off with was way larger than 1, right, and the closed loop gain depends on this quantity loop gain by 1 plus loop gain. So, as long as the magnitude of the loop gain is sufficiently large compared to 1, the what do you call the feedback loop is still effective. Okay. All right. So, basically, and that frequency, and at what frequency does the magnitude of the loop gain fall to 1? So, let us say this is f, this is the magnitude of the loop gain function in a log scale, this is a naught f at DC, and where is the 3 dB bandwidth of the loop gain? Omega naught. Beyond omega naught, it falls at 20 dB per decade, right. So, at what frequency does the magnitude of the loop gain become 1? Quick analysis. Okay, let me, before you keep sitting and wasting your time writing long equations, let me ask you one thing. At frequencies far away from the, I mean, first of all, is this unity gain frequency going to be close to omega naught or far away from omega naught? Far away. At frequencies far away from omega naught, which of these terms dominates? S by omega naught, right? So, at large frequency, loop gain of S is nothing but A naught F omega naught over S, correct? Okay. So, now take a look at it and tell me at what frequency what is the unity gain frequency of the loop gain? A naught F omega. All right. Okay. So, the unity gain so basically the unity gain frequency of the loop gain function also happens to be the closed loop bandwidth of the system, right. Okay. So, is the unity gain frequency of the loop gain function, which is the same as A naught F times omega. Okay. Next observation that I would like to make, what is the unity gain frequency of the forward amplifier? It is simply A naught F. Okay. A naught F times, where is F coming? Of the forward amplifier. Which is the forward amplifier? Which is the forward amplifier? Yeah, what is this transfer function? So, what is the unity gain frequency of the forward amplifier? A naught omega, right. So, what is the closed loop gain at DC? Approximately. What is the closed loop DC gain? Closed loop DC gain 1 by F. All right. All right. Now, what does this mean? Stare at those two and tell me. Yeah. So, the product of the closed loop bandwidth times the closed loop gain is A naught omega naught. Do you follow? Okay, which is nothing but the UGB of the forward amplifier. All right. So, basically if you want to get a higher closed loop gain, the closed loop bandwidth that you get is going to be small, and the product of the two happens to be equal to the unity gain frequency of the forward amplifier, right. This has led many people to believe that gain bandwidth product is a constant, right. That is only true, I mean that is what happens if you basically don't, if you simply mug up a formula without thinking about it, right. This is only true under these conditions that the formula was derived by, under which the formulae were derived, correct. That is, forward amplifier is first order system, a feedback block is basically memoryless. So, that the loop gain function is the first order system, in which case then it is true that if you attempt to increase the closed loop gain, you will basically reduce the closed loop, it will result in a smaller closed loop band. Does that make sense, people? All right.